The topic that we will discuss is types of relations. Before we move on to types of relation, let us recall the definition of relations. A relation R from set A to B is a subset of A cross B, and R is written as set of all order pairs A comma B, where A is member of A and B is member of capital B. Clearly, if A is related to B by R, by the condition given under R, then the order pair A comma B is always in the relation R, and we express A R B. That means A is related to B. Now, one thing we must note over here is, if it's written that R is a relation in a set A, okay, then it would mean that R is a subset of A cross A. So all the time it's not necessary that we have got two different sets. It may happen that both the sets are same. So in that case, R will be equal to set of all order pairs A comma B, where A and B belong to A only. So let us take one example over here. So here I have taken a set A which contains 1, 2, 3, and R I have defined as set of all order pairs for which the first component is either greater than B or equal to B. So by the definition of this, let us write down the elements for this relation. So we know that if R is a relation in set A, that means R is subset of A cross A. So first we write A cross A. So A cross A we have written down. Now we will write down the relation elements for the relation R. So here elements in relation R will be elements from here. We'll have some order pairs from here only, which would satisfy this condition. So we see that only these elements from here, only these elements will satisfy this condition. So we got the relation, okay, R, and domain for this relation will be the set of all first components of these order pairs. So 1, 2, 3, 1, 2, 3, and range will be the collection of all second components from these order pairs. So 1, 2, and 3. So here both domain and range are same. So here domain of R and range of R. Now let's move on to types of relations. So first we have empty relation and universal relation. So suppose we have a relation R in set A, then this relation R will be called an empty or void relation if R is equal to null set. Universal relation, suppose R is a relation in a set A, then we would say that R is a universal relation if R is equal to A cross A. Now next is identity relation. Now suppose R is a relation in set A, then R will be called an identity relation if every element of A is related to itself. If every element of A is related to itself, then that relation is called identity relation. So every element is related to itself. That means in that relation you will see every order pair has same first and second component. And if R is identity relation, then we denote that relation as I and A. Here this means it's an identity relation in set A. Now we have reflexive relation, symmetric relation, transitive relation, and equivalence relations. So let R be a relation in set A, then we would say that R is a reflexive relation if for every A in set A we have A comma A in R. Okay, so if R is a relation in a set and for every A we have A comma A in R, then the relation is called reflexive. Symmetric relation. Let R be a relation in a set A, then R is said to be symmetric if we have A comma B in R, then that would imply that B comma A is also in R. So in a relation, if you see for each ordered pair, this happens. Okay, that if you have A comma B in that relation, then you must find B comma A in R. Okay, and if this happens for each ordered pair appearing that relation, then we say that the given relation is symmetric relation. Next, transitive relation. Let R be a relation in a set A, then R is said to be a transitive relation if we have two ordered pairs of this type where the second component of this is equal to the first component of this. Then if we could find A comma C, if we can find an ordered pair which will be A comma C in that relation, okay, then we would say that relation is transitive. So if you have, suppose if you have two ordered pair of this type where the second component is equal to the first component, then we must have A comma C, then only we would say that relation is transitive. Okay, if it happens that for a pair of ordered pairs you don't get this, okay, like suppose you have A comma B and B comma C in relation, but you don't see A comma C in that relation, that means that relation is not transitive. Next, equivalence relation. Suppose R is a relation in set A and R is reflexive, symmetric and transitive. Okay, then the relation will be called an equivalence relation. Let us see example. Here I have taken a set A which has elements 2, 3, 4, and I have defined these relations R1, R2, R3, R4, R5, R6. R1 is defined as this, where sum of the first and second component should be equal to 8. For R2 I have defined the first component is less than equal to second. For R3 I have defined A is equal to B. For R4 I have defined A is greater than equal to B. For R5 I have defined absolute value of A minus B is greater than 0. For R6 I have defined A cube is greater than equal to B cube. We need to write each in roster form. So here A we have which has 2, 3, 4. Now I write down A cross A because I know that these are the subsets of A cross A. So it would be easy for us to write down the elements for each relation. So first one here, for the first, sum of the first and second component should be equal to 8. But here we don't see any ordered pair which would satisfy these conditions. So therefore R1 is a null set. Therefore this is an empty relation. Now next R2, for which the first A is less than equal to B square. Okay, and we see that each ordered pair of this A cross A satisfies this condition. Therefore R2 is nothing but A cross A only. Therefore R2 is universal relation. Next is R3. For R3, condition is A should be equal to B. So according to this condition we got these ordered pairs for this relation. So here we observe that for each element in A, okay, that means every element in A is related to itself. So therefore this relation is an identity relation. Next R4, here is defined as A is greater than equal to B. By this condition, we got these ordered pairs from A cross A. So here we notice that for every element in A, okay, they are related to themselves. Okay, like 2 is related to itself, 3 is related to 3, 4 is related to 4. Therefore, R4 is reflexive. R5 here condition is absolute value of A minus B should be greater than 0. So according to this definition, we got these order pairs, and here we notice that for each order pair, if I have 2 comma 3, then I have 3 comma 2 also. Okay, if I have 2 comma 4, then I have 4 comma 2 also. Okay, so you take any order pair and interchange their first and second component. Whatever order pair you get, you can see in R5. Like here 2 comma 4, interchange the first and second, so I get 4 comma 2. We will see 4 comma 2 is here. 4 comma 3, interchange them, and you see that 3 comma 4 is there. So this is happening for each order pair in this relation. So this relation is symmetric. Now next is R6. Here condition is the Q of first should be greater than equal to Q of second. So by this condition, we have got these order pairs from A cross A, and here we notice that if I have 3 comma 2, okay, and 2 comma 2, so here second component is equal to first component, so I've got 3 comma 2 also, that is here. If I have 3 comma 3, so second component is 3, and here first component is 3, so I've got 3 comma 2 also, it is here. If I have got 4 comma 2, second component here 2, here first component is 2, so if I have 4 comma 2 and 2 comma 2, then I've got 4 comma 2 also, this is the one. If I have 4 comma 4, second component is 4, here first component is 4, so I've got 4 comma 3 also, this is the one. So this satisfies the condition of transitivity. So R6 is transitive. Now we see an example for equivalence relation. Here we have taken a relation R, which is defined on set of integers, and here condition is that R will have all those order pairs for which this condition is satisfied. So x comma y belongs to relation R if x minus y is divisible by number 5. We need to show that R is an equivalence relation on I. So for that we need to show that R is reflexive, symmetric, and transitive. So here R is set of all ordered pairs for which x minus y is divisible by 5. So in order to show R is reflexive, we must show that every element of I is related to itself. So let us take an arbitrary element x belongs to I, then x minus x will be equal to 0, and 0 is divisible by 5. In fact, 0 is divisible by any non-zero number. So x comma x is a member of R for every x belongs to I. Therefore, R is reflexive. Next, we need to show that R is symmetric. For that, we take an element in R. An element in R will be an order pair. So here I am taking x comma y. It is in R. So R will be symmetric only if we could show that y comma x also belongs to R. So as x comma y belongs to R, then it satisfies the condition, and the condition is that x minus y is divisible by 5. So as x comma y belongs to R, so x minus y is divisible by 5. So this can be written as minus y plus x, because x and y are member of integers. So we can write it in this manner. Now next we can write minus in bracket y minus x. Clearly this is divisible by 5. If this is divisible by 5, that means this y minus x is divisible by 5. So as y minus x is divisible by 5, therefore y comma x will belong to this relation. Okay, that means y is related to x. Thus we were able to show that if x comma y belongs to R, that implies that y comma x also belongs to R. Therefore R is symmetric. Now we would show that R is transitive. For that we would take two order pairs in R. So x comma y and y comma z. We have to take such a way that second component of one is equal to the first component of the other. So here x comma y and y comma z I have taken. So as x comma y belongs to R, so this implies that x minus y is divisible by 5. So as x minus y is divisible by 5, that means x minus y is multiple of 5. So we can write x minus y equal to 5 times m, where m is an integer. Next, y comma z belongs to R. This implies that y minus z is divisible by 5. This implies that y minus z is multiple of 5. That means we can write y minus z is equal to 5 times some number. That number have taken n, and n will belong to set of integers. Now what we would do is we would add this x minus y equal to 5m and y minus z equal to 5n. So left hand side will be added, right hand side will be added. So here when you add left hand side, y minus y and plus y gets they will get cancelled, so you are left with x minus z, and this side 5 will come out as common, so you are left with 5 into m plus n in bracket. In place of m plus n I put p. Okay, so we see that x minus z is multiple of 5, therefore x minus z is divisible by 5. So as x minus z is divisible by 5, therefore x is related to y. So we can write x comma z belongs to R. So thus we were able to show that if you have x comma y and y comma z in R, that would imply that x comma z belongs to R. Thus R is transitive. So as R is reflexive, symmetric, transitive, hence R is an equivalence relation.